Hello everyone, welcome back to another remote sensing lecture video. And in this lecture video I want to talk about the supervised classification algorithms. Right, and so if you remember back to the first video in this module when we said that we extract the pixel values, and we have some like 67, 57, 22, right? So these are the pixel values. And that we were then comparing these were the classes, class 1, class 2, and class 3, right? We said that we were comparing, or there was a comparison, right? Comparison between the pixel values that we extracted for a given pixel, and we were comparing those to the different class options provided by the training data. Now, the algorithms, this is where we talk about the comparison. And I want to make clear that there are so many different options to do these sort of classifications, but we're going to talk about three. We're going to talk about maximum likelihood, support vector machine, and random forest. Okay, and so what I want to do to actually talk about each of these is actually something a little bit different. I think it's a lot easier to visualize these using computer-generated graphics rather than my terrible drawing skills. So I'm actually going to fade into a voiced-over PowerPoint going through these three different methods. It's going to be a slightly longer video overall, but I think it's going to be a little bit better of a way to go through this. Let's talk about maximum likelihood. So maximum likelihood is it uses mean, variance, and covariance in the training data to create a probability density that a pixel will be assigned to a certain class. And there's a lot of words in here, a lot of math terms that you may not understand. So let's just take a second here and let's walk through what each one of those means and sort of graphically what they look like. And then let's look at an image that shows you how maximum likelihood works and how it actually determines what classes different pixels go into. So let's start with variance. So in math, variance refers to how spread out the data is. And usually that's relative to the mean. So in this case, we have three different training data sets. We have a purple training data set, an orange training data set, and a green training data set. And so I'm sorry if this is slightly confusing with unsupervised classifications. In this case, this cross here is not a cluster center. It is rather the approximate mean of this data in both the X and Y. And the circle here is just to show you sort of the general trend of the data. So when we say something has high variance, what we're meaning is that if you plot it along the axis, that the range of values that covers is going to be high. So as you can see, when looking at band 1 for green, it's a relatively low variance, right? So if you squished all of these down onto the x-axis, it wouldn't go very far. It would go from like 15% to maybe 25%. But if you look at in band 2, right, it goes from like 30% all the way up to almost 100%. So it has high variance in band 2, but low variance in band 1. And you can sort of see how that looks almost like a rectangle, or an oval in this case. And then if you sort of rotated that 90 degrees, you'd have the orange training data set, which has high variance in band 1, right, because it goes from about 35% up to about 75, 80%, but it only covers about 15% in band 2. So it has a high variance in band 1, but a low variance in band 2. And then to contrast that with purple, purple has a relatively low variance in both band 1 and band 2. Now if the pixels had identical values, it would obviously have zero variance because there's no difference between it and the mean, because it would just be itself. So the second value that maximum likelihood uses is covariance. And covariance refers to how two variables change in relation to each other. So this really has to do with how they stretch along a diagonal line. So again, these are the same data sets. If we look at green again, we see that it, again, has high variance in the y-axis, right, in band 2, but low variance in band 1. But another way to interpret that is that it doesn't really matter what band 2 is. Band 1 doesn't change that much. So there's not a really strong relationship. Band 2 can be any number, and band 1 is going to be pretty much the same. The same thing can be said for band 2, right? It had high variance in band 1, but low variance in band 2. And that means that really it doesn't matter what band 1 is. Band 2 is still going to be more or less the same. So these two have low covariance because the values aren't changing. There's no discernible pattern to the change. So in contrast to this, we've now changed purple. And purple is now looks like this. And you can see that as you increase band 1, you also increase band 2. And so that means that there's a high covariance because as you increase band 1, you increase band 2. Band 2 co-varies with band 1 because there's this sort of diagonal relationship here. And the stronger that relationship is, the more diagonal that relationship is, the higher the covariance. The closer it gets to a perpendicular line, horizontal or vertical, the lower the covariance, right? Because you start to care less about what the other band is doing. Hopefully that makes sense. Hopefully visually this makes sense. The high covariance means that it's more of a diagonal. Low covariance means it's more of a straight line, either vertical or horizontal. So maximum likelihood takes those values into consideration and creates what's called probabilities. So in this case, each one of these circles represents a line of equal probability. And you can think about how the closer you are to the center, right, the fewer number of rings you are away, the more likely you are to belong to this class. So that's what probability means, right? Probability is how likely you are to belong to this class. So if you're inside of this first ring, you're really likely going to be orange, and that sort of visually makes sense, right? If you're 4 rings out, you're still likely to be orange, but maybe less so. So what maximum likelihood does is it simply looks and says, okay, well, where does this point fall in relation to all of these different probabilities? And we're going to look at an example of what that actually looks like graphically. So in this case, we have three data points. So these are new pixels from the input image that haven't been used in training. So we have a triangle, a square, and a star. And what maximum likelihood does is it looks at these and says, okay, well, this one is roughly 3 rings away from green, and I stopped drawing after a while because the probability would just have been low. So you can see this is going to go to green. On this one, it's 1, 2, 3, 4 rings away from orange. On this sort of pinkish color, it's only 1 ring. So it's closer, its highest probability, right? It's 40% probable that it's or it's 60% probable that it's orange. And it's 100% probable that it's pink, right? Because it's on the first ring of probability. So it's going to assign itself to pink. And this one does the same thing, right? It's 1, 2, 3, 4 lines away from green. It's only 1, 2, 3 lines away from orange. So it's going to say, okay, it's more than likely orange. And again, this is an artistic rendering, so this isn't, mathematically perfect to how it works. But you get the idea how it's all about these probability and the density probability. And so then if you look at it that way, that's exactly what happens, right? Triangle goes to green, star goes to pink, square goes to orange. So that's how maximum likelihood works, and I hope that made sense. The next option is support vector machine. So again, now we're getting into the machine learning algorithms that don't rely on those statistical measures. So what support vector machine does is it uses models to find functions that best separate the training data into classes. And when I say function, all I mean is an equation that draws a line. So you can think of this function as a line or a curve. And support vector machine has a special name for that called a hyperplane that separates the training data into classes. And what it does is it finds that function, right? It finds that line that maximizes the width between the function line and the training data. And we'll look at a couple images to sort of clarify what that means, what that looks like. And then pixels are assigned based on their position relative to that hyperplane. So if we just sort of quickly, this is a very basic two-case scenario, you can see that what we've got here is, again, we're finding a function that describes a line. So if we have the square class and the circle class, you can imagine that any number of lines could be drawn that would effectively separate these, right? This line here separates them. It's closer to square than circle, but it separates them effectively. This line separates them effectively, but it's closer to circle than square. What support vector machine does is it finds the optimal hyperplane, right? The best line here that creates this line so that the width between the line and the training cases is as wide as possible, right? This is the maximum width possible. And that's what support vector machine does. And then it compares new data relative to this sort of line here. So just to sort of show it on our stylized data set and show you that it isn't always necessarily just straight lines. In this case, this is our training data from before. We have these sort of hyperplanes here that separate the data. And you can see that we have our new data, so our square, our triangle, and our star. And all we do is we compare the lines. So these lines were created such that they created the maximum division between the data sets. So anything inside of here is orange, anything over here is light green, anything down here on this side of that line is purple. So you simply just look and say, okay, which side of the line is it on? So in this case, both triangle and square are in this sort of darker green, and star is once again in this pink. And so if you run the algorithm, that's exactly what you would get. Now, it's important to notice here that we've gotten a change here, right? Because if you remember back to maximum likelihood, square was actually part of the orange category, not the green. And so now you're going to say, okay, well, which one's better? And you can look at the data visually to maybe see what you think. There's definitely automated and sort of quantitative approaches, and we're going to talk in great detail about those in the next module when we talk about accuracy assessment. But for right now, just keep in mind that this goes to show you that not every single model will always give the same answer. And the model that you choose really does affect your results quite significantly. So let's talk about random forests. So support vector machine finds those sort of margins and hyperplanes and all of that. Random forest works entirely differently. What random forest does is it uses what's called classification and regression trees. So each tree is its own model, and then the forest uses hundreds or thousands of these trees to create the forest that it then uses to classify the data. And the way that it does this is it gives each one of those individual trees a subset of variables. So say your data has 15 bands. Each one of those regression trees may only get, say, 5 or 7 bands to work with, so that each tree is slightly different. And the idea here is that if you run your data through all of those trees in the forest, that you're going to get a majority of them saying one thing, and that majority is most likely the correct choice. And the way each tree works, and we're going to look at a tree here in detail in just a second, is that each tree consists of a number of nodes or levels. And you can think of each node as being a binary decision. So we're going to take the blue band and we're going to say, is the blue band greater than 50%? If yes, go left. If no, go right. And then if you went yes on the blue band, you then say, okay, well, is the red band less than 25%? If yes, go right. If no, go left. And you sort of continue down this sort of dichotomous branching tree until you get to the point where you're left with only one class's worth of training pixels. And then when you get to that point, that's a class. And then anytime a new pixel ends up there, it's assigned to that class, or it's voted to be in that class. And again, we're going to look at that in just a second to make things a lot more clear. So at a very high level, this is what random forest artistically looks like. So we have a bunch of different classification and regression trees. That's what each one of these sort of pyramid shapes are. And you can see that each one of the trees has these different nodes here, and each node has a binary decision, a yes or a no. And you can imagine that each one of these nodes has a data threshold, and we'll look at one tree in detail in just a second. But you can see that what you do is you would pass this new instance, so a new pixel, into here, and it would run down the tree. So it would be yes, 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 and it ends up here, which we're saying is class A. Then here it goes yes, 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 no, and it ends up in class B. And then here it goes yes, no, yes, and it turns out that this is also a class B node. So you see we have 2 votes for class B and 1 vote for class A. So you end up with a majority voting into class B, would be the final class for this particular pixel, run through all of the different classification and regression trees in the random forest. So now let's just take a closer look at one classification and regression tree and see what that looks like. So once again, up here we have our training data from before, so we have those 5 classes once again. And now we're going to figure out how we can use binary decisions to split this data up so that we end up in each unique class. So let's just take a second and let's look at the data. And we see that there's a really big sort of disparity between these 2 classes with low reflectance in band 1 and these 2 classes with high reflectance in band 1. And then sort of orange is somewhere in the middle, and you can even see that there's a little division here. So you might say, okay, well, let's just pick 50% in band 1 as a good threshold. So we'll say, is band 1 greater than 50%? If yes, we're over here. If no, we're over here. So if it is greater than 50%, so now we're over here, we say, okay, well, the other option we have is band 2. So if we look at band 2, we say, okay, is band 2 greater than 60%? We'll be up here. Is band 2 less than 60%? We'll be down here. So then we say, okay, if we're greater than 60%, which is like right here, we say, okay, so we're here. And as you can see, if we sort of draw a box, so this is greater than 50%, greater than 60%, all of a sudden, all we have left are the green training pixels. So now we are the light green class, and so this would be the class that if you get to, you'd be voted as that class. So now let's say we're not. Let's say we're not greater than 60%. So we're now under here. So now we're in this box here, where everything that is greater than 50%, but less than 60% in band 2. So we have a little bit of orange and a little bit of pink. So how do we split those? Well, we look at band 2 again and we say, okay, is band 2 less than 30%? If yes, now we're in here and we're in pink. If no, we're dealing with this half of orange. So we say yes, we say no, we go purple, we go pink or orange. So now let's go the other way and say, okay, well, it's not greater than 50%. So now we're over here, right? We're on this side. And we can apply the same logic. We say, well, is band 2 greater than 60%? Because if it is, we're dealing with everything above this line here, and we're dealing with the green class. If not, we're dealing with the other half of orange and purple. And so we could say, well, you could say, okay, well, is band 1 less than 30%? Or you could say, is band 2 less than 30%? That's really up to the model to decide. And in this case, it arbitrarily, and because this is an artistic rendering, chose to say, is band 2 less than 30%? And that splits it out. So you can see how if you ran new pixels through here, they would go through these decision-making processes and they would get voted into one of the 4 classes. So let's actually do that. Let's go through this tree with the same 3 data points that we did before, and now I've sort of attempted to assign them percentages. So you can see triangle is here. It's got 33% in band 1 and 80 in band 2. The square has 30% in band 1 and 65% in band 2. And then the star has 65% in band 1 and 27% in band 2. So if we run it through this algorithm, we see that let's just do triangle as an example. So it hits here. Is band 1 greater than 50%? The answer is no. So it goes to here. Is band 2 greater than 60%? The answer is yes. So it goes here. Right? So yes. So then you can see that we can do the same thing with diamond and star, and you would end up with the same results that we got from support vector machine. So hopefully this makes sense and how random forest works, and hopefully this makes sense on how classification and regression trees work. The math of how it decides what variable to use and what threshold to put in is a little more complicated than is important for this class, but what is important is to understand that fundamentally this is how these things work. And again, how these assigned in here are a little more complex in terms of the math. But hopefully, again, this makes sense. So let's talk about why you should use supervised classifications, right? It seems like it takes a lot of work to collect the training data and do all that kind of stuff. And the models seem a lot more complicated. But in reality, it's nice because it allows you to create classes that are immediately recognizable. And more important than that, you can focus in on classes that you think are important, right? Because with unsupervised classification, you had no control over what classes came out in terms of what they were. If you're interested in, say, an invasive species, and you run an unsupervised classification, right? That invasive species may occur in 5 different classes that you then would have to figure out, well, can I merge the whole class? Do I have to bust the class up because it's half invasive and half non-invasive before I can merge them? There's a lot more work that goes into that. Versus supervised classifications, you get really what you're looking for. And the other thing is that, at least in terms of support vector machine and the statistical ones especially, there's really no randomness. There's no random results. You can get the same result every time. Now, random forest obviously has some randomness, but the thing is you're using so many models that at the end of the day, your results shouldn't change too much with random forest. So let's talk about some reasons why you might not want to use supervised classification, or what some issues are that you could run into. Well, the first issue is maybe your classes just aren't distinct enough. Maybe you're interested in shallow water versus deep water, and the image that you have, you just simply can't distinguish between the two. And so you end up with error. Even though you want to get these two classes out, the image simply can't do it, even though you're giving it training data. And the other issue actually deals with training data, and we're going to talk about that in the next lecture video of this module. And maybe you just simply have issues with the quantity or the quality of the training data. Maybe you simply can't get training data for the classes that you want. Or maybe you get the training data, but it was collected on a GPS unit that's accuracy was so bad that it's, the person in the field was standing on next to a tree, but the GPS unit is so inaccurate that the actual point came out in the water. And so it's labeled as a tree in the training data, but yet it's coming out in the image as water. So those are really 2 major issues, just quantity and quality of training data. So what I'd like to do now is stop the video here, and then in the next lecture video, which will be in this module, we will talk about training data more in depth. So with that, as always, if you have any questions, please feel free to email me or go through Blackboard and contact me directly. And as always, thank you.